Welcome to this problem solving session number 5. In this problem solving session, we are going to discuss problems related to transmission line. So in this first problem, you are asked to find the capacitance and inductance per unit length of a coaxial cable transmission line. And you are asked to show that the speed of the wave in such a transmission line is V is equal to 1 by square root of mu epsilon. Mu is the permeability of the medium and epsilon is the permittivity of the medium. Okay, let us do it. First of all, we know that the transmission line is basically, it consists of two conductors in parallel, and coaxial cable consists of two concentric cylindrical conductors. So you have a inner conductor and you have a outer conductor. So you have, say we have a coaxial cable like this. This is the outer conductor and this is the inner conductor. Okay, and this coaxial cable has a circuit representation, and in circuit representation it is represented by a resistance in series with this inductor L, resistance R, and then we have this conductance. In the class actually we have taken a very simplified model of the transmission line, but if I go do it rigorously, then that's how we'll do it. We have a conductance and also we have this capacitance here. So here R is the total resistance of the coaxial cable, C is the total capacitance, L is the total inductance, Z is the conductance, total conductance. In fact, it gives the total, Z refers to the total leakage resistance, and in general R is considered to be very small. So in superconducting circuit we consider the transmission line to be nearly lossless, so therefore R is 0, and the conductance is taken to be very large, so very huge, so Z, this conductance tends to actually infinity. So under these two approximations, the schematic of the coaxial cable would be very simple. So we'll have a inductance and as well as we'll have this conductance only. So now let us go back to the given problem where we are asked to find out the capacitance as well as the inductance of this coaxial cable. So to do that, let me draw the coaxial cable again. We have this inner cylinder is there, and we have this outer cylinder. Let us say this outer cylinder has diameter capital D and the inner cylinder has diameter small d, and the length of the coaxial cable is say h. Okay, so let us say a charge q is there inside the inner conductor, and if I now draw a Gaussian surface, a Gaussian cylinder like this, and which has a radius say r, we know how to solve this kind of typical problem. So our here this radius is say r, then we can find out using Gauss law the electric field. As per the Gauss law, we have E dot dA. dA is the area element, that is equal to Q divided by epsilon. Epsilon is the permeability, permittivity, and mu is the permeability of the medium, that is the cylinder this coaxial cable is containing. And then here we will have E into 2 pi r H. Just look at the Gaussian cylinder here. So if you look at the, I'm talking about the Gaussian cylinder here. So then you have here Q by epsilon, and you know that electric field would be Q divided by 2 pi r h epsilon. Okay. Now what about the voltage difference? You just have to find out the voltage difference, because ultimately what is in my mind is to apply this formula that Q is equal to C into V. Thereby I will be able to find out the capacitance. So I need to know the voltage difference. So voltage difference would be EdR, and let us say you are going from the inner cylinder to the outer cylinder, and inner cylinder has radius d by 2, small d by 2, and the outer cylinder has radius capital D by 2. And if I put the expression for the electric field, so let us do it. So I have, if I put the electric field expression, so it is Q by 2 pi h epsilon 1 by r dr. So this is a constant term, so I can take it out, and then 1 by r dr, that is logarithm of r, and if I put the limits, then you will get this expression very easily, very straightforwardly. You will get 2 pi h epsilon logarithm of capital D by small d. So this is the voltage, and because we know that Q is equal to CV, so from here I can therefore write that capacitance would be Q by V, and this would give us 2 pi epsilon h divided by logarithm of capital D by small d. Now what about the capacitance per unit length? So that would be capital C by h. So I can write it as small c, that is the capacitance per unit length. That would be 2 pi epsilon divided by logarithm of d by capital D by small d. So this is what we have, capacitance per unit length of the coaxial cable. Now let us find out the inductance. To find the inductance, let us assume that inside this inner cylinder we have a current I, okay, and we have this outer cylinder. So we have to apply Ampere's law. To apply the Ampere law, let me draw an Amperean loop of say radius r. Then this has length is again h. So if I apply the Ampere's law, I know that Ampere's law is B dot dl is equal to mu I. Mu is the permeability. So this will give me B into 2 pi r is equal to mu into I. Okay, so therefore magnetic field B is equal to mu I divided by 2 pi r. And now what about the flux through the imaginary this Amperean loop? The flux phi is integral B dot dA, okay, and you have to take it from the limit, you have to go from the inner cylinder to the outer cylinder. So it is small d by 2 to capital D by 2, and if I put the expression for the magnetic field, I will have, I can take it out, mu I 2 pi h, let me take it out, and here I have dr by r. Integral limit is from small d by 2 to capital D by 2, and again in a similar way we know that this would be simply mu I h divided by 2 pi logarithm of d by small d. Okay, now what is the voltage drop? Voltage drop is actually, or that is the EMF. is equal to EMF is equal to minus d phi dt. So therefore this is d phi dt, and if I know the expression of phi here, so let me utilize it, and I will get it as mu h by 2 pi logarithm of d by d and dl dt. Oh, sorry, di dt, right? This should be, because this is the current, so I have di dt, and this EMF is actually equal to L di dt. Voltage drop across the inductance is L di dt. So if I compare it, so this will immediately give me the total inductance. That would be L is equal to you will have it as mu h divided by 2 pi logarithm of capital D by small d. And what about the inductance per unit length? That would be L by h would be equal to mu by 2 pi logarithm of d capital D by small d. So this is the inductance. So we have both the inductance and the capacitance per unit length we have worked out. So this is equation 1, and we have this equation 2. Now finally we are asked to find out the velocity of the electromagnetic wave there, or we already know from our transmission line discussion in our class that the velocity is equal to 1 divided by square root of small l small c. And if I put this, you will immediately get, you please check it, you will get it to be 1 by square root of mu into epsilon. Now let us do this problem. You are asked to show that the voltage travels with speed v is equal to 1 by square root of Lc in a transmission line. Here small l is the inductance per unit length and small c is the capacitance per unit length. Also work out the characteristic impedance of a transmission line. Let us do it. We learned that a transmission line without loss can be modeled by a series of unit cells comprising of inductance and capacitance like this. So we have, this is one unit cell, then we have a unit cell like this, and so on. Okay, this is lossless transmission line, and this is, say, inductance is L, inductance per unit length, let me take it to be L by H, and this is L by H, and this is capacitance per unit length, this is C by H, this is C by H, capital C by H, capital C by H, L by H, and so on. So we consider that this transmission line is extended, it's a one-dimensional transmission line, it is extended along x direction, so it is an infinite transmission line. And now let us consider a unit cell in the length delta x. Let me just consider only one unit cell like this. Okay, so say this length is delta x, this is L by H, which let me now write as small l, and this is small c. Small l is L by H, inductance per unit length, and small c is capacitance per unit length. Okay, now let's say here current I1 is flowing through it, and at this end the current is I2, and the voltage here is a V1, and the voltage across this here is V2, and a current is flowing through the capacitor, so that is a dq dt. the capacitor is getting charged, and here the voltage is V is equal to 0, this part is grounded. So in that case, the potential difference across the inductor would be V1 minus V2. That would be equal to, across the inductance has inductance L by H, and the length is delta X. So this is the total inductance. So L di dt we know. So this is the voltage difference. Let's say this is my equation number 1. On the other hand, difference in the current is I1 minus I2, that is across the capacitance. We have dq dt. This is what we have, and we know that we have Q is equal to CV. C is the capacitance, so total capacitance would be C by H into delta X, and here we have d V2 dt2. Okay, so this is, let us say it is equation number 2. So the potential difference delta V, I can actually write it as, because this is, I am considering it's a continuum kind of a transmission line. So though we have very small inductance and capacitance are there, so I can write the potential difference as V of x2 minus say V of x1 at two different location, and this I can write also as delta V by delta x if I divide it by the length. So from here, from this equation number 1, I can write it as minus, because I have taken Vx2 minus Vx1, unlike here it is V1 minus V2, so the sign would get changed. So therefore I have minus, I hope you are getting the idea, L by H. So delta X I am taking to the other side, so it will have L by H d, this would be I1 dt. Okay, now in the limit delta X tends to 0, we will have this, we can write del V by del X, we can write as del V del X, and that would be equal to minus L by H. Let me write it as small l now. I have del I del D. Okay, so this is, let me say, let me term it as equation number 3. Okay, similarly, again we can write the current difference, that is delta I, is equal to, again look at this equation, delta I can write it as Ix2 minus Ix1. Here I am writing it as I1 minus I2. Again you will get a sign, change in sign, so therefore I can write delta I by delta X is equal to minus C by H dV2 dt. Please look at this equation again here. Okay, so again in the limit delta X tends to 0, I can write delta I by delta X in the limit delta X tends to 0 as del I del X. That would be equal to this, let me write small c, capacitance per unit length, and here I have del V del T. Okay, this is another equation I get. So let me write these two equations separately. Basically we have two equations, one for voltage, how the voltage is changing with distance, then this is equal to L del I del T, and we have delta I delta X is equal to minus small c, capacitance per unit length, del V del T. So these two equations now we are going to exploit. Now if I take the time derivative of this equation, actually is not time derivative, space derivative with respect to x. If I differentiate on both sides, I will have del 2v del x2, that would be equal to minus L del t, let me write here del I del x, and from the this equation I can therefore write it as, this is minus, here another minus is there, so it would be plus LC del 2v del t2. So this is the equation for voltage, so I get del 2v del x2. Okay, actually it is pretty easy to see if you compare this equation with the classical wave equation, that is your del 2 f del x2 is equal to 1 by v square del 2 f del t2. From the classical wave equation, the velocity, so this is, don't get confused with this v, this is, let me say, capital V voltage, this is capital V, then the velocity, so that is small v, is equal to 1 divided by square root of LC. So you can easily, so you see the voltage travels in the speed of 1 given by 1 by square root of LC. Another way to look at it, because we know that this equation has a traveling wave solution, so V I can write it as A e to the power I kx minus omega t. So there is a traveling wave along the x direction. So if I put this solution V is equal to A e to the power I kx minus omega t in this equation, then you can see that you will get this dispersion relation, that would be k square is equal to omega square LC. If you put it, you will see that, and from here you can write omega by k, the magnitude would be, which is basically the velocity, and that would be equal to again 1 by square root of LC. Okay, now we are asked to find out the characteristic impedance as well. So to do that, let me go to this current equation here. I can, from this relation, I can write del I del t is equal to minus 1 by L del V del x. So now I know the solution for the potential. V is equal to A to the power I k x minus omega t. This one I have. So if I put it there, then I will get it as minus 1 by L I k A e to the power I k x minus omega t. Alright. So from here I can find out the current if I take the integral. So I will have minus 1 by L okay, let me first write the integral I k a integration e to the power I kx minus omega t dt, and if I do the integration, so you will get it. I am giving you a very simplified approach here, so you will get it as k by omega a e to the power I kx minus omega t, or from here, because I know what is omega by k, that is 1 by square root of LC, this I know. So if I put it there, so I will get c by small l square root of L a e to the power I kx minus omega t. So this is my current, and voltage also already I know, that is A e to the power I kx minus omega t. Now let us consider the voltage and current at any particular point on the transmission line. Now if we look at the picture of the coaxial transmission line, which has a inner cylinder as well as a outer cylinder. So let us say in the inner cylinder, at any given point here the current is say I of xt, it is going along this direction, along x direction, and its potential here is say v of x of t. And if the outer cylinder we consider that its potential is v is equal to 0, then the characteristic impedance is given by the ratio of the voltage at a given at a point divided by the corresponding current at that point, at a instant of time t. So v of xt is a e to the power I kx minus omega t, and current, already this expression we know, that is square root of c by l, small c by small l, a e to the power I kx minus omega t. So therefore z0 I can write as square root of small l by small c, which is also I can write as total inductance per unit length L by H, and here is total capacitance per unit length. So this is generally, this characteristic impedance is written as square root of capital L by capital C. So this is the well-known expressions for the characteristic impedance of a transmission line. Let us now work out this problem. You are asked to show the detailed derivation of the dispersion relation obtained in the process of quantization of the infinite transmission line. If you remember, we have actually done the quantization problem in lecture number 14, where I have shown you the process how to quantize it. Here I will actually fill up the gaps because I just give you the steps there, but here I will show you all the steps. The transmission line Hamiltonian, we wrote it in this form, that is summation over n pn square by 2c plus phi n minus 1. Phi is the magnetic flux, phi n whole square divided by 2l. L is the inductance, total inductance of the transmission line, and C is the total capacitance of the transmission line. And here phi n, this is equal to the sum over k. K lies between minus pi by a to plus pi by a, amplitude ak into ak, that is the annihilation operator, e to the power I kx plus ak dagger e to the power minus I kx. And the momentum Pn is equal to sum over k c into ak minus I omega k. Omega k is the angular frequency of the kth mode. Ak e to the power I kx minus ak dagger e to the power minus I kx. And because of translational invariance, we had ak is equal to a minus k, omega k is equal to omega minus k, and x is equal to n into a. N is the number of unit cell and a is the size of the unit cell. Now let us expand the terms in this Hamiltonian one by one. So first let me expand Pn square. So this should be, we will have now two sum over k's. Let us say one is k dash and another is k. So if I square it, I will have c square ak dash, and I will have I will go minus minus plus, so I square minus, so therefore I will have minus omega k dash, and here I will have ak Let me write it. Ak e to the power ikx minus ak dagger. All these are operators. Ak dagger e to the power minus ikx into ak dash e to the power I k dash x minus ak dash dagger e to the power minus I k dash x. Okay, now let me expand it. So here I will get k dash c square ak dash minus omega k dash. I will have ak dash e to the power I k plus k dash x minus ak dagger ak dash e to the power I k minus k dash x minus ak dagger ak dash e to the power minus I k minus k dash x. Then I have plus ak dagger ak dash dagger e to the power minus I k plus k dash x. Alright, now let us use the orthogonality condition. I talked about it in the class. Orthogonality conditions I have here as, say, sum over n k dash e to the power I k plus k dash x, that would be equal to w by a delta k minus k dash. That means when k is equal to minus k dash, we will get 1 here, and then sum over n will give you the total number of cells, and that is w by a. Okay, so similarly we will have another condition, that would be sum over n k dash e to the power I k minus k dash x, that would be equal to w by a delta k dash. Okay, these are the conditions that we are now going to exploit. So then what we are going to do, we'll get is this sum over n law. So pn square, this will give, so you just have to, this is difficult, maybe I have to make it scroll it again and again, but if you just write it on a piece of paper, that would be more useful. So let me now write down what you are going to get if you apply this orthogonality condition. You will get w by a summation over k and k dash c square ak dash minus omega k dash, and here you will get ak dash delta k minus k dash minus ak dash dagger delta k dash minus ak dagger ak dash delta k dash, and we will have finally plus ak dagger ak dash dagger delta k minus k dash. Okay, so this implies that I will get the term, the first term in the Hamiltonian, that would be pn square by 2c, that would be equal to 1 by 2c summation over k w by a capital C square ak square minus omega k square, and inside the bracket I will have ak a minus k minus ak dagger minus a dagger k ak plus ak dagger a minus k dagger. Okay, so this is what I will get. So let me say this is my equation number 2. So I actually worked out expanded the first term in our Hamiltonian. Let me now look at the second term. That means we have to now find out phi n minus 1 minus phi n whole square divided by 2l. So what is this? So let us work it out. Because we have phi l is equal to sum over k ak e to the power I kx plus ak dagger e to the power minus I kx. Okay, so we'll have phi n minus 1. This would be equal to sum over k ak e to the power, you see x is equal to n into a, so therefore let me exploit that here. Here I will have e to the power I k n minus 1 a plus ak dagger e to the power minus I k n minus 1 into a. Okay, so using this I can therefore write, it implies that phi n minus 1 is equal to sum over k ak e to the power I kx e to the power minus I ka plus ak dagger e to the power minus I kx e to the power I ka. Okay, very simple. So therefore we have phi n minus 1 minus phi n, that we can now work out, that would be equal to sum over k. You have here ak e to the power I kx e to the power minus I ka minus 1, and we have ak dagger e to the power minus I kx e to the power I ka minus 1. This I can further write as summation over k ak e to the power I kx e to the power minus I ka by 2. Then here I will have e to the power minus I ka by 2 minus e to the power I ka by 2 and plus ak dagger e to the power minus I kx e to the power I ka by 2 e to the power I ka by 2 minus e to the power minus I ka by 2. Okay, and you know that e to the power minus theta minus I theta plus e to the power, oh actually minus, okay, you know e to the power I theta minus e to the power minus I theta is equal to twice I sine theta. So we can use this identity and then put it in the expression, and we'll get this one. We'll get let me write the final expression. Finally, what you will get if you apply that, you will get phi n minus 1 minus phi n is equal to sum over k 2I sine ka by 2, and here you will have ak dagger e to the power minus I k x minus a by 2 minus ak e to the power I k x minus a by 2. Okay, so this is what I will get. Therefore, I have phi n minus 1 minus phi n whole square divided by 2l. So this would be equal to 1 by 2l. Now I have to take two sum over k's. One is a k, another one is k prime, and here I will have utilizing this expression. I will get, let me write the full thing. You will have 4 minus 4 sine k a by 2 sine k dash a by 2. You will have ak dagger e to the power minus ik x minus a by 2 minus ak e to the power ik x minus a by 2. Okay, this is one term, and you have to multiply it with ak dash a dagger k dash e to the power minus I k dash x minus a by 2 minus ak dash e to the power I k dash x minus a by 2. Okay, this is basically algebra. Now let me expand it. Okay, let me do it. What I will have here, I will have minus 2 by L sum over k and k dash sine k a by 2 sine k dash a by 2, and in the bracket I will have ak dash. You will get several terms, ak dagger dash dagger e to the power minus I k plus k dash x e to the power I k plus k dash a by 2, and you will have minus ak dash ak dagger ak dash e to the power minus I k minus k dash x e to the power I k minus k dash a by 2, and you will have minus ak dash ak dash dagger e to the power I k minus k dash x e to the power minus I k minus k dash a by 2, and finally you will have ak dash ak dash e to the power I k plus k dash x e to the power minus I k plus k dash a by 2. As you can see, these are tedious algebra, but you have to just very simple. You have to keep on doing it systematically, then you will get the results. Now apply orthogonality condition. As we discussed earlier. So if I do that, you have to sum over n phi n minus 1 minus phi n whole square by 2l. So you will get minus 2 by L w by a sum over k ak square, and here I will have minus ak dagger minus a minus k dagger sine square ka by 2 minus ak dagger ak sine square ka by 2 minus you will get ak dagger sine square ka by 2, and you will get finally minus ak minus ak a minus k sine square ka by 2. So these are the terms you will get. So okay, let me therefore finally write that I will get summation over n phi n minus 1 minus phi n whole square, these are operators, divided by 2l is equal to 2 by l w capital W by a sum over k ak square sine square ka by 2, and here in the bracket you will get ak dagger minus a minus k dagger plus ak dagger ak plus ak dagger plus ak a minus k. Okay, so this is what is the second term in the Hamiltonian. Let me say this is equation number 3. We had equation number 2 also. Yes. So now let me put this expression 2 and 3 in our original Hamiltonian, that is here. So if I put it, then I will get my Hamiltonian as this. Putting 2 and 3 in 1, we will get the Hamiltonian as actually let me give you the, after doing bit of algebra, you will get W by A AK square, okay, and you will get terms like this minus omega k square by 2c plus sine square ka by 2 by l is also there. You have a minus k, a minus k, and you will have terms plus ak dagger plus ak dagger ak, that would be multiplied by omega k square c by 2 plus 2 by l sine square ka by 2, and you will have a term like minus omega k square by 2 into c plus 2 by l sine square ka by 2 ak dagger a minus k dagger. Okay, now you see these terms, this term and this term is not, we don't want these terms, these are unwanted terms, and therefore we take minus omega k square by 2 c plus 2 by l sine square ka by 2 to be equal to 0, and from this we get the required dispersion relation, that is omega k is equal to 2 by square root of l into c sine modulus of ka by 2. So this was the dispersion relation I mentioned in the lecture classes. Okay, now again let me quickly show you, because now these two terms are 0, these two terms are not there, so we can write our Hamiltonian as sum over k W by a ak square omega k square into C, and here I have ak dagger plus ak dagger ak, which further I can write as summation over k w by a ak square omega k square C into, this would be twice ak dagger ak plus 1. I think all of you are getting it because I have just utilized this commutation relation ak dagger is equal to 1. So this is what I utilized to write it, and I can therefore write it as 2w by a ak square omega k square C ak dagger ak plus half. Okay, now if we take, that's what we did in the class, taking h cross omega k is equal to 2w ak square omega k square C divided by a, we can write the Hamiltonian in the usual harmonic oscillator form. That would be summation over k h cross omega k ak dagger ak plus half.